startup companies in biotechnology, whereby they can have access to wet lab facilities, be it facilities for molecular biology, bioprocessing, or analytics, things that they can't normally afford with these startup funds that they have. We have one company, they are able to make a biofertilizer delivery system. You could have a small amount of fibers which is dipped, let's say, in a cup this size, and this could give biofertilizer to as much as 1 acre of fertilizer land, which would normally take a truckload.
Hello and welcome to our IRIS webinar today. My name is Ujwala Koti and I work at the Office of Global Engagement at IIT Madras. Our speaker today is Dr. Abhishek Sinha, who is an assistant professor in the Department of Electrical Engineering at the Indian Institute of Technology, Madras. Dr. Sinha received his PhD degree from the Massachusetts Institute of Technology in 2017, where he was associated with the Laboratory for Information and Decision Systems, LITS. He is a recipient of the Best Paper Award in Infocom 2018 and the Best Paper Award in Mobihawk 2016. Professor Gnansaran Chatterjee Memorial Gold Medal and T.P. Saha Memorial Gold Center Silver Medal from Jadavpur University and Jagdish Bose National Science Talent Search Scholarship, Kolkata, India. His areas of interest include networks, information theory, theoretical machine learning, and applied probability. Dr. Sinha, I welcome you to today's webinar, and over to you, sir.
Thanks for the kind introduction. Is my screen visible? Can you see my the slides?
Not yet, not yet.
Okay, so let me try sharing it again. All right, it should be visible now.
Yes, it's visible now.
All right. Okay. So good evening, everyone. It's an honor to give a talk on this forum. So today I'll be talking about some ongoing research initiatives in our lab on intelligent resource allocation in large-scale networks. So I'll start with a witty code made by the famous information theorist Thomas Cover from the Stanford University. So he quipped, "Theory is the first term in the tailored series of practice." Put another way, the most direct way to study and improve the performance of a system is to construct simple mathematical models for it and analyze them rigorously. Of course, this may leave out some second-order practical effects, but the knowledge gained from such an analysis often sheds valuable insight into the design of high-performing system. So following this roadmap, in our lab, we tackle some of the most fundamental problems in resource allocations in large-scale networks. In particular, while designing algorithms or analyzing a system, we focus our attention on 3 fundamental metrics, namely efficiency, robustness, and intelligence. Efficiency determines whether a particular algorithm utilizes system resources in the most optimal fashion. There is a uniformly desirable criterion. One of the main technical questions that is relevant here is how to design an algorithm that is capacity achieving. On the other hand, robustness determines whether a particular algorithm works well when the operating environment itself is perturbed. In most practical applications, the system parameters remains uncertain and changes over time. So practical algorithms need to be robust against the change in the environment. Finally, there is a growing emphasis on algorithms that can adaptively learn from the past and choose future actions in an intelligent fashion. So in the following slides, I'll illustrate how our work addresses each of the questions in our specific problem instances. So I'll start with a line of research where the objective is to design a scalable capacity achieving algorithm for large scale networks. As a motivation, think about the following problem. How can we enable hundreds of millions of streaming IoT connections across the internet without causing a traffic jam on the internet superhighway? So this is indeed a pressing problem. So formally consider the following system model. Assume that several nodes are connected by either by wired or wireless links of limited capacities. External packets arrive to the nodes randomly at some unknown rate lambda. The problem is to design a dynamic routing and scheduling algorithm to efficiently transport the packets from their sources to their destinations. So next, I'll give some details about the possible types of packet flows. One type of flow could be the usual unicast traffic, having a single source and a single destination. In this case, for each packet, the algorithm first determines a path from the source to the destination and then routes the packet over the chosen path. The flow could also be the multicast or broadcast type, where a packet needs to be replicated across all or some of the nodes in a network. This type of flow is common in defense applications where live information needs to be streamed across a group of nodes, say UAVs. In this case, the algorithm first determines a suitable tree and then transmits the packets along the tree. Note that since packet replication is involved, unlike unicast, there is no flow conservation with the broadcast flow, and this makes the problem theoretically challenging. So it is obvious that network flow is a fundamental problem, but until recently, there is no capacity achieving known algorithm that is dynamic, that is known for this problem. So let me now explain the principal mathematical difficulty in designing such an algorithm. So consider two tandem queues. There is a very simple system. We have two tandem queues where packets arrive to the first queue independently at random. They get serviced then and then enter the second queue. So it is not difficult to see that although the arrivals to the first queue are independent, the arrivals to the second queue are not. They are very much correlated. So not surprisingly, analyzing this system becomes intractable for arbitrary network. So this begs the following question. So instead of analyzing the original system that we are given, so can we instead consider another simple relaxed system and design a control policy for that relaxed system and use that policy for the original system and show that it probably works? This looks like an ambitious project. In particular, the first question that we need to resolve is that which constraints we are going to relax without losing much. So the answer to this question, it's a fundamental question and it turns out to be quite metaphorical. We relax one of the most fundamental tenets of causality, known as a precedence constraint. In other words, we allow the packets to travel in time in a mathematically constructed proxy of the system. So again, so let me be more specific. So consider the following network. Suppose the packet needs to be transported over the links 1, 2, and then 2, 3, and finally 3, 4. Physically, the packets cannot be transported over the links 2, 3 until it has been sent over the links 1, 2. To get over this difficulty, we consider a mathematical system where this constraint is simply not present. Hence, an incoming packet is simultaneously pushed into all three queues on its path as soon as it arrives. So we have an effectively parallel system of virtual queues with IID arrivals and which is amenable to theoretical analysis. So one of our main results is to prove that it is enough to design a stabilizing policy for the virtual system only. So in particular, the stabilizing policy turns out to be as follows. So route packets along the shortest path or tree weighted by the virtual queue lengths, and for wireless networks, schedule non-interfering links having the maximum total virtual queue lengths. So we prove that this policy, along with a suitable packet scheduling discipline, is indeed capacity achieving. So this is established by combining techniques from Lyapunov methods as well as adversarial queuing theory. So a paper for coming out from this project received the Best Paper Award in Mobile 2016 held in Germany. So this routing policy is not only theoretically optimal, it also achieves very good performance compared to the state-of-the-art benchmarks. From the plots, we see that the proposed policy achieves 2x reduction in delay while operating at 90% of the network capacity. So it is indeed remarkable. Now I will go to the second part of the talk where I talk about the robust algorithms. So I'll now present a robust scheduling algorithm for 5G networks with provable performance guarantees. The motivation for this problem comes from the following question. So how to reliably deliver real-time information to a centralized control over unreliable wireless channels? Broadly, we are interested to looking to design policies that are reliable against adversarial environment and simultaneously achieve near optimality in more benign environments. So we want the best of the both worlds. So as a concrete example, consider this particular cellular communication setup. We have n users moving around in an area having n base stations. Due to the wireless scheduling constraint, the base station can communicate with only one user under its coverage at a slot. However, contrary to the usual model, where the channel and the user mobility is described by some long-term statistics, in our work, we assume that the channel states and the user mobility can be completely arbitrary from slot to slot, and which may even be controlled by an adversary. So this is a realistic model for 5G where the channel changes rapidly in a high-speed environment due to beam misalignment. So designing robust algorithm in this adversarial wireless setup is a very difficult task as it departs radically from the classical stochastic model. So, okay, what is our objectives? Our objective is the users are interested in keeping up to date with the latest information. We can immediately see that there is a clear trade-off between two conflicting goals. Each user wants to communicate with the base station as often as possible, but due to the resource constraints, only one transmission can be scheduled at a time. Furthermore, arbitrary user movements and the adversarial nature of the channel makes the design of this policy very challenging. So we considered a simple greedy policy which schedules every user at every slot, which is the most stale information. In other words, this policy gives priority to the user who has the most delayed information at a slot. This is the most backlogged user. And we now present results on the performance of the proposed greedy policy in this adversarial setting. The performance is given in terms of a quantity called the competitive ratio. The competitive ratio measures the performance of any online policy against a clairvoyant optimal policy which knows all featured information. Naturally, we prefer a competitive ratio which is as small as possible. From the table, that is given here, we can see that the proposed policy, the greedy policy, achieves a finite competitive ratio which is within a logarithmic factor of the best online policy in the case of a PKH metric. So this is indeed good. So the policy is indeed good. Now let's see how this policy performs in the more benign stochastic setting. So here we assume that the stochastic model where the channel from the IIT user to the base station is modeled as a binary erasure channel, right? So in this following table, we see that a similar index policy achieves an average freshness within a factor of 2 of the optimum. So in the case of peak freshness, the proposed policy is actually optimal. The take-home point is that we have designed online scheduling policies that can operate reliably against adversarial environment and achieves near optimality in the more benign stochastic setting. And now I'm coming to and this received the Best Word Award in 2018 held in Honolulu, Hawaii in the USA. Now I come to the final part of the talk, the algorithms for prediction and learning. So I focus on algorithms that learn from the past and make predictive decisions. So as a motivation, assume that you are an engineer in Netflix. You have hundreds of millions of subscribers, and at any point of time, a subscriber may want to stream any arbitrary movie or show. Now, as new shows emerge, the distribution of the requested contents from the subscribers, they can change very fast. So to meet this demand, what Netflix does, the Netflix maintains thousands of geo-replicated caches across the globe. A user may retrieve content from multiple caches within its reach. Our objective is to dynamically prefetch the contents on the caches so that the number of cache hits is maximized. Note that the algorithms need to be robust as they learn the request pattern in an online fashion, and we do not assume any underlying probability distribution of the request sequence. They could be completely arbitrary. So schematically, the problem can be represented as a bipartite caching network as shown in this diagram. So unfortunately, unlike the previous problem where we show that the greedy strategy works, in this problem it doesn't. So if we greedily load the caches according to the past frequency counts, it simply doesn't work. It doesn't yield a stable caching algorithm with a sublinearity gradient. So however, very surprisingly, the simple tweak to this thing works. So if we add independent Gaussian noise to the frequency counts of the files and optimize the caches accordingly by solving an LP suitably constructed, the resulting algorithm provably learns against an adversarial request pattern. So in a recent paper, we show that the proposed learning-based policy is regret optimal up to a factor of n to the power 3/8, where n is the number of users. The proof of this result combines ideas from various disciplines, including combinatorics and combinatorial optimization, probabilistic methods, and statistical sampling theory. So here is some experimental results. So the proposed policy also performs very well with the real-world data set. We experimented the CDN trace consisting of around 375K requests We randomly generate a network with 30 users and 15 caches, and from the plots, you see that the proposed learning-based caching policy outperforms the existing state-of-the-art algorithms by a huge margin. In fact, it achieves almost 2 times the hit rate over the state-of-the-art policy. So going forward, what we would like to do with this IOE and with our center, proposed center of excellence. So we want to design an interpretable, provable, and scalable learning algorithms for large-scale networks. So it should have an impact on emerging paradigm of federated learning. We are also looking forward to design robust and agile communication schemes for rapidly varying environments. So it has applications in strategy communication, cognitive review, and for self-driving cars. And we are also looking at the do some fundamental investigation on online prediction and learning. So it has impact on edge caching, load balancing on data centers, etc. Would like to fine-tune and deploy algorithms in real-time systems and characterize their real-time practical performance. So for this, I'm looking to recruit students at the master's, PhD, and postdoc levels. So the applicants should have a solid background in mathematics, statistics, algorithms, or theoretical machine learning and related disciplines. If interested, directly send an email to me with your resume, the most updated resume. So with this, I would like to thank you again, and I'd like to answer any question that you might have. So let me see Q&A. So, sir, how will time travel with humans will take place? Okay, so okay, I'm not talking about the time travel here. I'm talking about constructing a mathematical system, right? That operates in the principle like where you do not have any precedence constraint. So it is a mathematical system. So it's not a physical system. So this is a kind of abstraction of the physical system. And if we design algorithms for that particular system and use the same algorithm in an original physical system that doesn't enjoy this precedence relaxation property, we show that it still works. So I'm not going to design time travel algorithms for the human, right? So this is a mathematical system. So this is called the relaxed system that we constructed here. If you're interested, please write me an email, and I'll just send you the relevant papers. It's a very interesting question and interesting algorithms indeed. Okay, so sir, how can we fine-tune the algorithms in real time? It's a very interesting question. So the algorithms, for example, we are in the era of AI and ML, right? And the algorithms that you should right now design it should not require any hand tuning of the parameters. The algorithms should learn all these things by itself, right? So by the learning, so the algorithm should be adaptive, so that it should learn from the environment and it will tune itself, right? For example, think about the caching problem. So we do not make any assumption. We didn't make any assumption on the underlying file request sequence. So even if your file request sequence is changing with time, the algorithm will adapt it itself, right? So we do not need to fine tune the algorithms. If you need to fine tune the parameters of your algorithm, that's bad. So think about how can we actually improve upon that. All right, next question, sir. Can artificial intelligence equipments control network crashes in India? So definitely, yes. So as I said, for example, look about, so let's say adversarial attack, right? So think about a DDoS attack. So the question is, how can we detect such an attack, right? And the way we actually design or some algorithm for detecting this attack is using AI, using ML principles. So definitely, if you can detect this attack, you can prevent it. So AI equipments, definitely it can be used to provide a seamless service, and it can definitely be used to make networks fault free, right? So next question, how can one apply for the PhD? Do one has to send the resume to you? Okay, so the PhD, please go to our department website. It has the detailed instruction on how to send your applications. You have to appear for the interview and so on and so forth. And if you want me to take a look at your resume so that I become interested in you, please send your resume and we can talk about it in detail. All right, any plans of using graph neural networks? Yes, surely. Why not? So whatever. So right now, this is neural networks are just kind of function approximator, right? So if you think that certain problems can be modeled using a graph neural network, this function can be approximated better by a graph neural network, we can actually go for it. But here I'm not using neural network algorithms here. So to be more specific, I'm using online learning algorithms. So we have an OCO policy, the technical digital online context optimization. So this doesn't use neural networks, right? So we are not using any function approximator for that, but the field is wide open. So you can use a graph neural network if your problem requires that. Would you please explain the CDN trace? Yes, right. So CDN trace is actually the Wikipedia trace, right? So this is a very big data set. I forgot the size, but it's more than 50 gigs, and it is available publicly. And to know where this the links and stuff, please send me an email, or I'll just search for this paper. The paper has all those details on how to. This is hosted on GitHub. And so this CDN trace actually longs four different metric. One is the user ID, the another is file ID, and another is the file size, and the last and the most important the log that it has that is useful for us is the time of the time of the day where the user actually requests that file. So this is how we actually use the CDN trace, and it is available online. So if you want to take a look at that, please take a look at this paper where I will give a link to that particular trace. Okay, so all right. So I think okay. All right. So there are many questions. Okay. So which programming languages is best for machine learning and artificial intelligence in upcoming years to come? Okay. So here, of course, I mean, you can use whatever learning, whatever languages you feel suitable. I mean, you just learn that. But you see, this learning these languages, this is not a fundamental thing. You should always focus your attention on learning the mathematics, learning the algorithms. These languages, these technologies will come and go. This is something that you can easily pick. So what you should focus is learning the actual algorithms, the mathematics, the fundamentals, right? So please explain independent Gaussian noise to frequency. Okay, so this indeed it's a good question. So I have not explained it fully. So this is known something called the follow the path leader. So where you add some Gaussian noise or you add some any noise, okay, with non-zero support, and to get rid of these adversarial attacks, right? So if you are interested, this is known as FTPL, follow the pattern leader policy. I'll urge you, take a look at that. Or if you want, just send me an email. I can explain to you better. So this is used for, to make sure that the adversary doesn't harm you much. So you're playing, you're doing some coin tosses, right? And the adversary doesn't know the outcome of your coin tosses, so that whatever strategy this adversary has, that might not be so much harmful to you. So this is the basic idea, but the mathematical idea, it requires some background before I explain that. Okay, this is known as follow the pattern beta policy. Okay, so how can AI equipments control network issues when it is in heavy traffic crashes and it is solved? I'm not very sure I understand this question. How can AI equipment control a network issues when it is okay? So all right, okay, so whatever I understood that, okay, so let's say part of this network is compromised, and how can I actually recover from this fault or from this crash, right? And how can you use AI for recovering that? So the thing is that, so think about multipath routing, right? So let's say I want to go from the source to the destination, and I have several paths by which I can take. And let's say there is an adversary, and the adversary is sabotaged some of the links on your path. The question is, you can measure the delay, right? Let's say you send some initial control packets, and you measure the delays on each of these packets, right? And from these delays, delay is going to be a random variable. It depends on many stuff, including the load as well as delay per each link. And from this, you measure it, right? And now you can actually run an algorithm, let's say regression algorithms, or for determining which path has been compromised and which path is still good. So based on that, you can route your traffic on the path that is good, that is not compromised. So this is something that you can do using AI, right? This is a very trivial way of solving this problem. There are many more efficient and more intelligent version of this same thing available, right? Now, okay, so could you explain the advantage of described routing algorithm compared to conventional methodology Bellman-Ford algorithm? This is a very good question. This is a very good question. So the Bellman-Ford algorithm, what it does, it gives you, let's say, the shortest path, right? But here I'm not looking at the shortest path routing. I'm looking to achieve the capacity of a network, the information theoretic capacity of this network, and so that it is not enough for me to just go along the shortest path, because there are multiple paths available, right? There are multiple paths available, so a good algorithm should, take advantage of all the paths that is available to you, all the degrees of freedom. So the question is, how do you actually, okay, so there could be exponentially many paths. Okay, in a general network, there are exponentially many paths. So the question is, how do you actually take advantage of that? How do you plan your routing in such a way that it achieves the theoretical capacity of this network? Right? So this is how this is different from the traditional Bellman-Ford algorithm, right? And or the max flow algorithm in particular, because, and also here we take a look at the wireless counterpart of this network. So in wireless networks, what happened, you cannot activate all the links simultaneously because of something called the wireless interference constant. Our algorithm takes care of that, and the Bellman-Ford algorithm, by definition, it cannot, or any Maxwell algorithm, by definition, it cannot. You need another scheduler, link scheduler for that. So if you're interested, please take a look at our transaction networking paper. Just send me an email, and we can discuss it in detail. Okay. What should be the most useful application of this technology, and under which sector would it count or crash? Which technology? You mean? Okay, so before I go to that, let me just, can we make routing intelligent in the context of IoT? Yes, absolutely. So that is a goal. That is a goal, right? Routing and caching. How do you actually do this routing and caching in an intelligent fashion? For example, in the context of IoTs, where there are billions of nodes, right? So billions of the small devices connected to the network. So how do you actually do that intelligent fashion? So it is definitely, let me come back to this question, because this is not something that I think I understood this question. What would be the most useful applications of this technology? Which technology? Okay, so this networking, or this, as I said, this, let's say the IoT is one of the, industrial control is one of them, right? For example, if you are talking about the age of information, so this is a very new metric that take a look at the freshness of the information, right? How fresh is this information? And this freshness of information metric is very important when, let's say you're interested in, let's say, knowing the score of a game, right? So what happens? So let's say game is in progress, and at every time point, what you want to know, you want to know the latest score, right? So the score keeps changing at every slot, at every second, and you want to know the latest score. But like you, all of your friends are also interested. But we have a limited capacity wireless network. So which means if the base station is sending information to you, it cannot send the information to your friends. But unfortunately, all of us are fighting for that scarce resources, right? So the question is, what is the best algorithm? What is the best way for the base station to determine which particular friend to serve, which particular friend to send information to? So this is okay. So this is just a figurative application. This is also very useful in industrial IoT applications, where let's say you're controlling a hazardous chemical plant, right? And maybe some sensor goes off, right? And this sensor information needs to be sent to the control center, so that the control center can take some action, right, to rectify that, right? So this is everywhere. Okay. In terms of UMW, yes, universal max weight. Universal max weight is a capacity achieving algorithms, right? It's a capacity achieving algorithms. It achieves a maximum rate. So you're given a network. What is the maximum rate? Mbps. You can send your information from the source to the destination. And not only unicast traffic, where it has a single source and single destination, you'd also like to broadcast packets, right? For example, think about, so for any given network, for any given engineering application, you would like to squeeze out the last bit of it, right? What is the maximum rate at which you can send this information? So in general, in any network application where you do care about the bit rate, where we always care about it, we always want the fastest internet connection possible. So there, this sort of technology, these algorithms are definitely useful. So this is a fundamental algorithm. So this is useful everywhere. Okay, so questions keep coming, lots of questions I see. Okay, how does RL work? Explain with an example. Generally, a reinforcement learning. Okay, so if you really want to know how an RL work, you need to you should take a course on RL. But how RL works? RL is basically it learns. So let's say if you know what Markov decision processes are, so you're given some state and some actions, and you have some goal, some objective, right? And you'd like to take your actions, and whenever you take in such a way that your long-term goal or long-term objective is maximized, right? So this is a general setup of a Markov decision process. RL is a particular kind of MDP, a particular problem variation of this MDP, where you do not know the transition probabilities, right? So you need to, you want to do some exploration versus exploitation. You want to learn the transition probabilities in such a way so that your ultimate objective is maximized, right? So this is how, okay, so this is a say problem set of our reinforcement learning algorithm, a reinforcement learning problem. And now there are multiple different algorithms available. So, but all of these algorithms, what they basically do one thing. It is exploitation versus exploitation. First they explore, so kind of estimate the transition probabilities, and then they exploit. So once you know the transition probabilities kind of accurately, what is going to be your best action, right? So this is how this reinforcement learning algorithms work. But again, this is a very vast topic, so I cannot do justice to it in 2 minutes. But this is how, I mean, this is the basic idea of how RL works. Cluster computing, type of cluster computing. So I don't think this question is complete. Could you please simplify optimal policy and elaborate? Yes. Optimal policy in the context of EMW? Yes. So think about a virtual system where you do not have any precedence constant. So basically you have a sort of parallel network, but this parallel network is mathematically constructed. This doesn't exist out there physically. So this is mathematically constructed. So this is something that you can simulate, right? And I design an algorithm for this particular simulated network. And this, how this algorithm works, this algorithm actually computes the shortest path. But the shortest path is not like Bellman-Ford shortest path. This shortest path is weighted shortest path, and the weights are computed by something called the virtual queues that you actually simulate. And depending on the type of traffic, depending on whether it's a unicast traffic or multicast traffic or broadcast traffic, you choose your paths or trees accordingly. So this is how this thing actually works. The EMW policy works, and this is probably the first policy, and it was designed by me at MIT almost 4 years ago. And this is the first policy that is universal, in the sense it can achieve capacity for unicast, broadcast, multicast traffic. So previously people knew how to do it for unicast traffic. The famous algorithm is known as back pressure, but this EMW kind of, which is very different from back pressure, and it's a more general, it's a universal policy. Okay, all right, so it looks like the last question. Okay, so this is not a technical question from computer science, currently focused on machine learning related electives. What electives from electrical engineering should I take to work later? I did industrial research on industrial IoT. Okay, so again, it's a very, I mean, it's very difficult to give a blanket answer to it. But if you ask me, the best thing is whatever you do, take the fundamental courses, take the math courses, take the algorithm course. Do not focus solely on the technologies, right? Or just learning the languages and so on and so forth, because these things will change and it will not provide you the value. The thing that will provide you the fundamentals, the mathematics, the algorithms. So focus on that, and this will be beneficial for you in the long term. Yes, either industry or research. Yes, obviously take courses on probability, take courses on information theory, convex optimization, and stuff like that. So this will definitely be beneficial, both in industry as well as in research. All right. So I think I have answered all the questions, and my time is also up, looks like. Okay. So I would like to over to you, Richu.
All right, thank you. Thanks a lot, Professor Abhishek Sinha. You've taken a lot of questions and answered all of them so patiently. Thank you for joining us at the webinar. And thank you to all the participants here. We do have 2 more webinars coming right up after this. One by Professor Geeta Krishnan Ramadure, and following that is Professor Nirav Butts. You could please join those webinars as well. Thank you to everyone.
Sure.
Yeah, thanks everyone.
Thanks.
Thank you. Bye.
Bye.